Hey guys, welcome to my channel. My name is Lokesh. I work as a lead architect in one of the unicorn companies called Fractal Analytics. So in this video, we'll again continue our book reading series. With this time, we'll be shifting to a new book. Remember, guys, we are not reading the entire books. We are just reading some snippets or some chapters of the books where we can get information about Gen AI. We can learn the terminologies so that whenever we are given a chance at work to work on AI tools, technologies, we should be able to contribute as well as help the team. Not only help, also gain some experience, exposure out of it. So, with that said, let's look into this uh, video, which book we are going to cover. So this is a famous book by the author called Chip Huan, and the book goes by the name of AI Engineering. So remember, guys, especially if you're coming from a data background, you might not be doing, a core Gen AI development work, which means that you might not be involved in the building the models, the LLMs, because that would need a different set of skill and enormous experience. Not only experience, you should be able to have the academic qualification in order to do that. So that is like a steep learning curve. So if you want to become that, then I think you will have a great challenge in front of you, and that would cost time and efforts. So our transition is like more organic, where we are already working on data engineering aspect. So transitioning to AI engineering makes sense, and both of these streams go hand in hand. Some of the topics and implementations get overlapped, but some might require a data engineering team or a dedicated AI engineering team. So coming back to the book, so you can see here this is AI engineering book, and we'll be covering the last chapter of this book. Although as you can see, some of the chapters I have covered some of the very fundamentals. So I would strongly recommend that you go through this book. You can maybe purchase a hard copy of this book, or you can subscribe to O'Reilly platform and try to get a subscription, and that way you will be able to access the book. So, and there are various topics in this book like introduction to building AI applications, understanding foundation, evaluation methodology, evaluate AI systems, prompt engineering, RAG. But what we'll be covering here is AI engineering architecture and user feedback, as we have done in the past, that we break down each paragraph that we go through. We'll try to do that. We'll take the help of Gemini in order to search for certain concepts, topics, and that is the way we'll be able to build upon this. So let's get started. I will close the contents section. Then you can see here chapter 10, AI engineering architecture and user feedback. So far, this book has covered a wide range of techniques to adapt foundation models to specific applications. This chapter will discuss how to bring these techniques together. Given the wide range of AI engineering techniques and tools available, selecting the right ones can feel overwhelming. Yes, to simplify this process, this chapter takes a gradual approach. Okay, that makes sense. It starts with simplest architecture for a foundation model application, highlights the challenges of that architecture, and gradually adds components to address them. You'll spend eternity reasoning about how to build a successful application, but the only way to find out if an application actually achieves its goal is to put it in front of users. User feedback has always been invaluable for guiding product development, but for AI application, user feedback has an even more crucial role as a data source for improving models. The conversational interface makes it easier for users to give feedback, but harder for developers to extract signals. This chapter will discuss different types of conversational AI feedback and how to design a system to collect the right feedback without hurting user experience. So this just they're just the author is just laying out what is expected out of this chapter. One thing would be interesting to know, guys, is to um, would be to find out whether any real application would be developed here, or it would be mostly, on the theoretical part of the art architectures. Because when the author says that you will have some user feedback, I'm assuming that maybe we'll be building something, a kind of a product or an application where the users should be able to play with that, and then they'll be able to give feedback based on that. So for that to happen, you need to have some sort of application. So let's start, but that's okay. We can start further, or we can continue further. AI engineering architecture. A full-fledged AI architecture can be complex. This section follows the process that a team might follow in production, starting with the simplest architecture and progressively adding more components. Despite the adverse diversity of applications, they share many common components. The architecture proposed here has been validated in multiple companies to be generally for a wide range of applications, but certain applications might deviate. In its simplest form, your application receives a query and sends it to a model. The model generates a response which is returned to the user. There is no complex augmentation, no guardrails, and no optimization. The Model API box refers to both third-party APIs and self-hosted models. Building an inference server for self-hosted model is discussed in Chapter 9. So you can see here this is a very simple architecture where user submits the query, and that query, as an API, calls the model API, and then it generates the response. These could be model APIs, or these could be self-hosted models, or models hosted in um, different environments and different, or hosted by different organizations. Because apart from OpenAI, Google, Anthropic, which are like the closed models, they only provide the API. You will have something called model hosting as well, where you can use an open source model and maybe host it in your environment, or maybe you can, if it's not open source, you can pay for the licensing, and then you can use it in your environment. So Databricks does that for the Llama models. Llama models are the models that are provided by Meta, which is nothing but the new name of Facebook. And those models are there. You have an option of hosting those models in Databricks. So that is where I'm able to do the comparison. So let's continue. From the simple architecture, you can add more components as needs arise. The process might look as follows. Enhance context input into a model by giving the model access to external data sources and tools for information gathering. Okay, so enhancing the context. Put in guardrails to protect your system and your users. Okay. Add model, router, and gateway to support complex pipelines and add more security. Optimize for latency and cost with caching. Add complex logic and write actions to maximize your system's capabilities. Okay, I think some of these things are being explained below. So let's look into that. Step 1, enhance context. The initial expansion of a platform usually involves adding mechanisms to allow the system to construct the relevant context needed by the model to answer each query. As discussed previously, context can be constructed through various retrieval mechanisms, including text retrieval, image retrieval, and tabular data retrieval. Context can also be augmented using tools that allows the models to automatically gather information through APIs such as web search, news, weather, events, etc. So what happens is whenever you type in a prompt, let's say, I want to uh, understand something about DeepSeek company. So usually, I would be writing a question in a single sentence or maybe a couple of sentences. But you will need to give more information to the LLM so that it can do a good job and get you the right result. So that is what is called context. So some of the times this context can come from some of the external websites. On other occasions, if you want the information, if you are prompting and you are using Gemini for the data that your company has, or the data or your personal data, in that case also you could use I mean you can enhance the context. So that is something we need to understand. So we'll take a pause here and we'll then continue. So let's continue. So second paragraph says context construction is like feature engineering for foundational models. It gives the model the necessary information to produce an output due to its central role in the system's output quality. Context construction is almost universally supported by model API providers. For example, providers like OpenAI, Claude, and Gemini allow users to upload files and allow their models to use tools. Context construction like feature engineering for foundation model. Okay, we understand what is feature engineering, which is then drawing features out of data. Gives the model the necessary information to produce an output. Your center on systems output quality context construction is almost universally supported. But why they're calling it similar to feature engineering? Because these are two separate concepts for me. Context construction is basically providing all the information to LLM, to foundation models rather. So LLMs would be when you have an LLM. Sorry guys, I'm just thinking out loud. So you have an LLM, you retrain that LLM, then there are various architecture patterns whether you want to fine tune it. And fine tune, you provide the features to it and do experimentation on that. But how is it similar to in context creation? Context construction is passing the input data to LLM. Okay, so maybe when you're doing the context construction, there could be some features that you might need to generate at runtime or real time, and that's why they're calling it as similar to feature engineering. So maybe let's Gemini this. Let me open gemini.google.com and we'll just copy this sentence, and then we'll write question why the author is calling context creation similar to feature engineering. Let's see what it is. The author is drawing a parallel between foundation model feature engineering and traditional machine learning. Transforming raw data just like feature engineering transforms raw data into a format for table information. Context creation takes raw information and structure it in a way that the foundation models can understand and utilize, enhancing model performance. Essentials in essence, both context engineering are about preparing the input data in a way that maximize the model ability to learn and perform it. There is a similarity when model API provides prioritized context features. Yeah, still not fully confident why context creation is similar to feature engineering. Maybe, I need to understand this concept more clearly with this context creation construction. I thought that this is just like, when you give a prompt. So there could be some, context related to that prompt. Yes, we can say that it is similar to preparing the data for the LLM so that they can give you the right output. But feature engineering is like, drawing features from the input data when you're training the model. So maybe the difference is context construction happens in real time, whereas feature engineering, this might happen when you're trying to train your model. That might be the difference. However, just like models differ in their capabilities, these provide differ in their context construction support. For example, they might have limitations on what type of documents and how many you can upload. So let's continue, guys. So we were going through the enhanced context. So the author is saying the context construction is like feature engineering of foundational models. We discussed about it. We're not able to exactly find the root analysis on why context construction is similar to feature engineering. Maybe because both of these processes or methods involve data collection and passing the data to the LLM so that the LLMs can make a better decision. So that could be the reason behind it. But let's move forward. However, just like models differ in their capabilities, these providers differ in their context construction support. For example, they might have limitations on what type of documents and how many you can upload. A specialized RAG solution might let you upload as many documents as your vector database can accommodate, but a generic model API might let you upload only a small number of documents. Different frameworks also differ in their retrieval algorithms and other retrieval configurations like chunk sizes. Similarly, for tool use, solutions also differ in the types of tools they support and the models of execution, such as whether they support parallel function execution or long-running jobs. So just break it down. So if you're an architecturing a RAG system or designing a RAG system, which is retrieval augmented generation, you have to think one thing in mind, that is RAG systems will use only the data that you provide. It will not use the entire data from the internet. It will only use the data that is available. So what the author is saying is, if you have a RAG system, you can upload as many, you can have as many data as your vector DB supports, because vector DB is where your encoded chunks of documents would be stored. Whereas if it comes to calling the API, it might be limited to the number of documents you can upload. A simple example is this Gemini interface. You can see here it gives the option to add files. But how many files we can add, that I'm not sure. Let me just try. I'll not try it, but that is understood. Because this is limited, there should be a limit on the number of documents you are uploading. There is an important question that is coming in my mind. How the RAG systems are different from the add files functionality that you see in ChatGPT or any other um, Gen AI applications. Because in RAG systems, you upload the document to the vector DB, and that is where the retrieval happens. That means those documents are encoded. So maybe let me ask my question is, if you have guessed it already, if you've not guessed it already, rather, when we upload documents through a Gen AI API model, does those get encoded? For example, in Gemini, if I upload a document and ask a question based on that, how does it work? So let's see, what it comes up with. When you upload a document to Gemini, it goes through a few key steps to be understood and analyzed by the model. Gemini first extracts the raw text from the document. This might involve OCR if the document is a scanned image or PDF embedded. Encoding the insight is then encoded into a format that the model can propose. Process this typically involves converting words and other textual into numerical. Okay. Storage: the document is stored in a way that allows for efficient that might involve indexing document, creating a vector DB. Contextually, when you ask a question based on document, Gemini uses a query to identify. So uploading a document to Gemini involves encoding it to a machine-readable format and storing it for efficient retrieval. When you ask a question, the model uses your query to retrieve this process allows. Okay. So which means that this is similar to RAG then. So what is the difference? What's the difference from RAG systems then? Okay. While both Gemini's document aim to incorporate functional encoding in Gemini, when you upload a document in Gemini, it handles the encoding internally. It uses its own mechanism to convert the document into suitable. In RAG, you have more control over the encoding. You typically choose your context retrieval. Gemini automatically retrieves the relevant context from the uploaded document based on a query. Often, to fine-tune the retrieval process, you can experiment with different retrieval methods. Retrieval are not transparent to the user model architecture. Gemini is a monitoring model that incorporates the knowledge from the uploaded document directly into its internal representation. Use a separate retrieval model to fetch relevant information from then fed to a generator model which flexibility. Gemini offers a more streamlined user-friendly experience but with extra flexibility. Okay, so more or less the process is same. That is, if you have a document, that document will be composed of chunks, and you if you have to store that into a DB because you want to fetch information from that document, you need to then do something called encoding, which is nothing but the numerical representation of the text. Now, in case of RAG systems, you can choose the first of all the embeddings or the encodings that you want to use, and then maybe uh, how you retrieve the data from that. You can do experimentation on top of it, because if it is not retrieving, the correct answer, maybe you can change it, fine tune it, so you have more, what you say, command over it. You have more customization over it. Whereas when it comes to Gemini, it is designed to give the users the real-time experience. So it essentially follows the same process, but you will not have any customization. So there could be hallucination when the answer is returned from Gemini, and that is the reason uh, the RAG systems should be proposed, where the real-time experience is not required. And also in RAG systems, you can, as we just discussed, in RAG system you can store lot of documents, but in Gemini or any UI where a real-time experience is required, maybe in those places will not be able to save lot of documents. So that is one thing. Different frameworks also differ in their retrieval algorithms and other retrieval configurations like chunk size. Similarly, for tool use, solutions also differ in the type of tools they support and the modes of execution, such as whether they support parallel function execution or long-running jobs. Different frameworks also differ in their retrieval. So I think they're talking about RAG systems. Similarly, for tool use solutions, why they are using tool here. Similarly, for tool use solutions also differ in different types of tools. Yeah, maybe this particular sentence, I'm not clear on this, what the author is trying to say. Let's move on with context. Construction, the architecture now looks like below. Let me see, why we have this context here. So first of all, the author suggested us a simple architecture where you will have a query and a response. From the simple, you can add more components. Okay, so these are the components that you can add on top of it. And so you now have a context construction. And then with the architecture looks like this. Databases, documents, tables, chat history, vector DB, read-only actions, vector search, and SQL queries, web search. So your context would now become meaningful, which means that you can either retrieve documents from the databases like VectorDB, or you might have structured and unstructured data. If you have structured data, then you should be able to add the SQL queries, web search, vector search. If you have unstructured data, put in guardrails. Guardrails help mitigate risks and protect. So what we are trying to do now is we are, or actually, in fact, the author is trying to build layers or add components on top of the vanilla architecture that was suggested. Guardrails help mitigate risks and protect you and your users. They should be placed whenever there are exposures to risks. In general, they can be categorized into guard lists around inputs and outputs. In general, they can be categorized into guardrails around inputs and outputs. So guardrails, I think these will especially come into picture that you don't want insensitive data or profanity, both in terms of what questions are being asked and in terms of the output that is being returned. Because remember, guys, LLM have access to the data of entire internet. Okay, so in the internet you will have a lot of other things like you will have um, profanity, you have profanity websites. So that whatever system that we design, especially if you're designing it for a client, we have to make sure that these guard rails are put in place. Input guardrails typically protect against two types of risks: leaking private information to external APIs, okay, and executing bad prompts that compromise your system. It discusses many different ways attackers can exploit. So there was a chapter entirely dedicated to it. While you can mitigate risk, they can never be fully eliminated due to the inherent nature of how models generate responses as well as unavoidable human failures. Leaking private information to external APIs is a risk specific to using external APIs, model APIs, when you need to send your data outside your organization. This might happen for many reasons, including the following. An employee copies the company's secret or uses private information into a prompt and sends it to a third-party API. This can happen. An application developer puts the company's internal policies and data into the application system's prompt. Okay. A tool retrieves private information from an internal database and adds it to the context. So with the tool here is refers, I think tool here refers to collecting information from other systems or databases without you writing in the context. But still, that does not explain why you have parallel function execution. Maybe the information that is being fetched to generate a context, that is a process actually. So that process could be streamlined in a way that you have one sub process after the another in a sequential manner, or you could have it in a parallel manner. So let's come to this. There is no airtight way to eliminate potential leaks when using third-party APIs. However, you can mitigate them with guardrails. You can use one of many available tools that automatically detect sensitive data. What sensitive data to detect is specified by you. Common sensitive data classes are the following: personal information like ID numbers, phone numbers, bank accounts, human faces, specific keywords and phrases associated with the company's intellectual property or privileged information. Many sensitive data detection tools use AI to identify potential sensitive information, such as determining if string resembles a valid home address. If a query is found to contain sensitive information, you have two options: block the entire query or remove the sensitive information from it. For instance, you can mask a user's phone number with placeholder. If the generated response contains this placeholder, use a PI reverse dictionary that maps this placeholder to the original information so that you can unmask it. So I think this paragraph is self-explanatory. There is nothing more to add. Maybe you can go through this figure, use a query. I got on this website, what did I do wrong? I mask query, I got 403 error on this code. What did I do wrong? Secret token that shouldn't be leaked. Okay, so this is how get access token. The URL you provide contains in text the correct masked query. Okay, so this is a way to specify the query. So you can see here while asking the query, the user has specified the secret token, and the here the that token or secret is being masked. And then model response. The URL probably contains the syntax. The current should be here is a correct version of your code. So this is a model response in case of masked query. And then the correct version. This is in case of masked. An example of masking and unmasking PII information using a reverse PI map to avoid sending it to external APIs. Output guardrails. A model can fail in many different ways. Output guardrails have two main functions: catch output failures. So this is the case of input. Specify the policy to handle different failure modes. To catch outputs that fail to meet your standards, you need to understand what failure looks like. The easiest failure to detect is when a model returns an empty response when it shouldn't. Failures look different for different applications. Here are some common failures in the two main categories: quality and security. Quality features, quality malformated responses that don't follow the expected output format. Quality malformated responses that don't allow the expected output format. For example, the application expects JSON and the model generates invalid JSON. Okay. Factually inconsistent responses is hallucinated by the model. Generally bad responses. For example, you ask the model to write an essay and that essay is just bad. Okay. Security toxic responses that contain racist content, sexual content, or illegal activities. Responses that contain private and sensitive information. Responses that trigger remote tool and code execution. Brand risk responses that mischaracterize your company or your competitors. Recall that for security measurements, it's important to track not only the security failures but also the false refusal rate. It's possible to have systems that are too secure, example one that blocks even legitimate responses, interrupting user workloads and causing user frustration. Okay. Yeah, we have to have guardrails, but it shouldn't be that tight that you're not getting the desired answer. So there should be some flexibility in that, and that is like walking on over the edge of the sword because uh, we've seen some of the companies, especially Meta, where people are bound to ask these questions, right, about race and all that. So how do you identify whether it's a genuine racial uh, comment, which is having an evil intent, or it's a genuine one? So that is something that has to be taken care of. But having said that, if you have airtight security, one thing is for sure that your data will not be compromised and you will not get any unwanted answer that you would have maybe gotten if the security was not that uh, airtight. So in those cases, I think that should be okay because if the false refusal rate is low, you can live with that. But if the false refusal rate goes high, then obviously, as the author is saying, the users will get even frustrated and they might not want to use the system. So many failures can be mitigated by simple retried logic. AI models are probabilistic, which means that if you try a query again, you might get a different response. So that's a good thing. Yesterday, during my work meeting, I heard about this term called deterministic. So I think it's deterministic versus probabilistic. Sorry, maybe I pronounced it wrongly last time around. Probabilistic, which means that if you give a question, AI model would return a different answer at the same time. It may return the same answer every time you try, but that's just a chance, and that is where the probability comes into picture. For example, if the response is empty, try again X times or until you get a non-empty response. Similarly, if the response is malformatted, try again until the response is correctly again. This retry policy, however, can incur extra latency and cost. Each retry means another round of API calls. If the retry is carried out after failure, the user perceived latency will double, obviously. To reduce latency, you can make calls in parallel. For example, for each query, instead of waiting for the query to fail before retrying, you send this query to the model twice at the same time, get back two responses, and pick the better one. Better strategy, good strategy. This increases the number of redundant API calls while keeping latency manageable. So this is a good strategy, guys. So this all happens under the hood. As a user, you will not be able to clearly, make a distinguish or make a distinction. For example, if I type in something here and I got a empty response, now I'm not actually they're not showing it to me, but in the backend, what would happen is maybe they would have followed that strategy that they would have sent two questions on one API call. And if one of the questions answers that were returned were non-empty, they would have, rendered it to me rather than rendering the blank one. So, and if there were two answers, then it would have given me the correct answer. It's also common to fall back on humans for tricky requests. For example, you can transfer the queries that contain specific phrases to human operators. You can do that. Some teams use a specialized model to decide when to transfer a conversations to human. One team, for instance, transfers the conversation to human operator when their state sentiment analysis model detects angers in users' messages. Another team transfers the conversation out a certain number of turns to prevent users from getting stuck in a loop. Again, self-explanatory. Don't have to explain much here. Guardrail implementation. Guardrails come with trade-offs. One is the reliability versus latency trade-off we just discussed. If you want the answers to be reliable, obviously you will have to wait for a longer time, and that is where the latency, will increase. This this is where I always get confused. What is latency? If latency is high, does that mean that the wait time is high? So let me just Gemini that. What is latency? Delay before. Okay, yeah. So you should always reduce the latency. While acknowledging the importance of guardrails, some teams told me that latency is more important. That teams decided not to implement guardrails because they can significantly increase the application's latency. The teams did not to implement. Teams decided not to implement guardrails because they significantly increase the application's latency. Okay, which is not good. Output guardrails might not work well in the stream completion mode. By default, the whole response is generated before being shown to the user, which can take a long time. In the stream completion mode, new tokens are streamed to the user as they're generated, reducing the time the user has to wait to. The downside is that it's hard to evaluate partial responses. Unsafe responses might be streamed to users before the system guardrails can determine what they should be blocked. So let me ask Gemini, give me an example of stream. What is that? Stream completion mode applications. Completion. So stream is like what you see on your window. So since you'll be able to see one word at a time and not the entire question, this is what means stream completion mode. And that is where the output guardrails would be difficult to implement, because if you're getting one word at a time, the systems will not know, or the guardrail systems will not know what was the actual context of the entire sentence or the paragraph which is being returned. So let's see whether it gives an example of this or not. In some is a way of processing data streams where the entire output is generated. Okay, we understand that. It's important. Batch processing of streaming data, applications requiring final results, situations where incremental updates are not needed. Yeah, maybe I was looking for some, UI application, but that's okay. Okay, new tokens are streamed to the user. Okay. Okay. How many guardrails you need to implement also depends on whether you're self-host your models or use third-party APIs. Very important. While you can implement guardrails on top of both, third-party APIs can reduce the guardrails you need to implement, since API providers typically provide many guardrails out of the box for you. At the same time, self-hosting means that you don't need to send requests externally, which reduces the need for many types of input guardrails. Given the many different places where an application might fail, guardrail can be implemented at many different levels. Model providers give their models guardrails to make their models better and more secure. However, model providers also have to balance safety and flexibility. Restrictions might make a model safer, but can also make it less usable for specific use case, which we have just seen. Guardrails can also be implemented by application developers. Many techniques are used in defense against prompt attack. Guardrail solutions that use out-of-the-box include Meta's Purple Llama and NVIDIA's Guardrails. So these are different kind of guardrail solutions. Due to overlap of risk in input and output, a guardrail solution will likely provide protection for both inputs and outputs. Some model gateways also provide guardrail functionalities as discussed in the next section. With guardrails, the architecture looks like below. Okay, so now you have guardrails. Now the architecture would look like this. So you added the context in the context construction in the previous section. Now you have input guardrails, then you have output guardrails. So you have scoring here. Input guardrails, personal information redaction, output guardrails, safety verification, structured outputs. Cool guys, so we'll limit our discussion till here and we'll continue with this. It's a fascinating chapter and a book. As I told you before at the start, it's you know it has become famous, especially in LinkedIn. Chip has become famous, but to be honest, it has given me a window into how should I go about uh, this um, technology that is AI engineering, this new field. Especially if you come from data engineering, you should maybe test out the waters with respect to AI engineering because that is, as I said, organic. So I hope this video was useful. I studied a lot and I hope you also gained something out of it. So we'll meet in the next video, guys. Till then, take good care of yourself and thank you for watching. Bye, guys.